Welcome back to Talk Tensors, everybody. Today we're going to be looking at trajectory prediction. Really interesting stuff and super important for all sorts of intelligent systems, like self-driving cars, robots, anything that needs to navigate a complex environment, really.
Yeah, absolutely. We're talking about predicting where things are going to move, like pedestrians, vehicles, even those delivery robots we see popping up everywhere these days. And it's not just about predicting movement in a vacuum. It's about understanding how those movements interact in busy, dynamic environments.
Right. And that's where this paper we're diving into comes in. It's called Trajectory Prediction Framework with Intention-Guided Contrastive Clustering. And it's taking a pretty unique approach, wouldn't you say?
Yeah. Definitely. It's all about intention, right? This idea that to really predict where something's going, you got to try to figure out why it's moving that way in the first place.
Okay, so it's like instead of just looking at the past motion and extrapolating like, oh, this car's been going straight, so it'll probably keep going straight.
Exactly. It's saying, well, maybe the car is going straight because it's trying to get to that intersection up ahead, or maybe it's going straight because it's about to make a right turn, but it's signaling and waiting for an opening in traffic.
So how do they actually go about capturing this intention thing? It seems pretty abstract, right? Like, how do you even define it?
Well, the paper breaks it down into a few basic categories like straight, left, right, and static. But the key is they acknowledge that these categories are kind of fuzzy. Like a gradual left turn might start out looking a lot like straight.
Yeah. And people don't always move in these perfect straight lines or perfect curves, right? They might hesitate, they might change their mind, they might get distracted.
Exactly. So the authors use this technique called contrastive clustering. Basically, it allows the model to group together trajectories that are similar, even if they don't fit neatly into those predefined intention categories.
Ah, I see. So it's like the model can learn that a hesitant left turn is still more similar to a smooth left turn than to, say, a sudden stop.
Exactly. That's what makes it so cool, this ability to learn these nuanced relationships between different movement patterns and how they relate to intention. And all of this with a very efficient model, I should add.
That was actually going to be my next question. Like, how computationally intensive is this whole process?
Well, that's one of the things that really impressed me about this paper. The authors are really focused on keeping things lightweight, which is crucial for any real-world application, right? You can't have a self-driving car trying to run some massive neural network in real time. It's just not practical.
Makes sense. So how do they achieve this efficiency?
Okay, so instead of using these massive, super complex deep learning models, they primarily rely on multi-layer perceptrons, or MLPs. They're basically these simple feed-forward neural networks.
So they're ditching those recurrent neural networks like LSTMs that are often used for sequence modeling tasks. Like those are pretty standard for dealing with time series data, right?
Yeah, they are. And the authors acknowledge that. But they argued that these RNNs can be a bit too computationally heavy for this particular application. They're saying, look, we've already got all this information about the agent's past trajectory and their likely intention. Why not just use a more streamlined approach to predict the next few steps?
I'm following. So instead of using an RNN to keep track of the entire sequence history, they're using MLPs to make predictions based on a kind of snapshot of the current state, along with the inferred intention.
Yeah, that's the gist of it. Now, that doesn't mean it's simple, right? They've still got some really clever design choices going on within the architecture.
Well, let's unpack that architecture a bit, shall we? What are the main components of the intent framework?
All right, so they break it down into 4 main modules. First up, you've got the observation feature extractor. Pretty self-explanatory, right? It takes that raw trajectory data, the sequence of X and Y coordinates over time, and converts it into a set of features that the model can actually learn from.
So not just the raw coordinates, but like more meaningful representations of the movement.
Precisely. They calculate things like the velocity between each point, the heading orientation. They even do a coordinate transformation to normalize the trajectories.
A coordinate transformation, huh? What's the purpose of that?
It's basically a way to make all the trajectories comparable regardless of their absolute orientation in the environment. They calculate the angle between the start and end points of the observed trajectory and then rotate everything so it's horizontally aligned.
Ah, that's clever. So it's like if you're trying to compare the shapes of different handwritten letters, it's easier if they're all oriented the same way.
Yeah, exactly. The transformation helps the model focus on the underlying pattern of movement, regardless of whether the agent is moving north, south, east, or west.
I like it. Okay, so they've got those velocity features, the heading orientations, the transform coordinates. Anything else they extract at this stage?
Yes, during the training phase, they also assign an initial intention label to each trajectory. They have an algorithm that looks at the extracted features and tries to classify the movement as static, straight, left, or right.
Ah, so that's how they give the model some initial examples of what these intentions look like in terms of those numerical features.
Right. But it's important to note that these ground truth intention labels are only used during training. When the model's actually making predictions on new data, it doesn't have access to those labels. It has to infer the intention solely from the observed trajectory.
Okay, so the feature extractor has done its job. We've got these nicely processed features. What happens next?
Next up is the representation learner. This module is all about learning a more compressed and abstract representation of the trajectory that captures the essence of the movement and crucially, the underlying intention.
And this is where those MLPs come in, right?
You got it. They use separate MLPs to encode each of those features. We extracted the velocities, the headings, the transformed coordinates, and then they combine those encoded features into a unified representation, which they further process to generate the final representation and the predicted intention.
So the representation learner is essentially learning to map those low-level features into a space where similar intentions are clustered together, right?
Exactly. They're training it using a classification loss, so it's encouraged to produce similar representations for trajectories that have the same ground truth intention label.
All right, so we've extracted the features, learned a representation that hopefully captures the intention. What's the next step in this pipeline?
The next module is where it gets really interesting, the intention clusterer. This is where they use contrastive learning to refine the model's understanding of intention.
Contrastive learning, huh? Refresh my memory on that one.
Sure. It's this idea of learning by comparing. You basically train the model to distinguish between similar and dissimilar examples. In this case, they're comparing pairs of trajectory representations based on their predicted intentions.
So like trajectories where the model predicts the same intention would be considered a similar pair, and trajectories with different predicted intentions would be a dissimilar pair.
Precisely. And the model is trained using a contrastive loss function. It tries to pull the representations of similar pairs closer together in the embedding space and push dissimilar pairs further apart.
So even if the initial intention labels were a bit off, this contrastive learning process helps the model fine-tune its understanding of intention based on the actual patterns of movement in the data.
Right. It's allowing the model to discover these more nuanced relationships between different types of movements, even if those relationships weren't explicitly captured by those initial labels.
That's pretty cool. Okay, so we've got a refined understanding of intention. Now we need to actually predict where the agent's going to go. That's where the location predictor comes in, right?
Exactly. The location predictor takes the end location of the observed trajectory, that learned representation from the representation learner, and the predicted intention, and it uses all that to predict the agent's future locations step by step.
And this is where they're doing things a bit differently, architecture-wise, right? They're not using RNNs here.
Yeah, they're sticking with those efficient MLPs. For each future time step, they have a dedicated set of MLPs that process the input information and generate a predicted location. They even use a simplified LSTM-like structure, but without the actual recurrence between time steps. It's just a clever way to incorporate some of the benefits of an LSTM without the computational overhead.
So each time step is kind of treated independently, but they're still able to incorporate information about the intention and the overall trajectory history into those predictions.
That's right. And the predicted intention actually acts as a kind of weighting mechanism, influencing the likely direction of movement based on what the model believes the agent is trying to do.
Got it. So they train this location predictor to minimize the distance between the predicted locations and the actual locations from the ground truth trajectories, right?
Yep, that's the gist. They're using mean squared error, or MSE, as the loss function for the location predictor. And remember, the entire intent framework, from those initial feature extractors all the way to the final location predictions, is trained end to end. That means all the modules are learning together, optimizing for that overall prediction accuracy.
All right, so we've talked about the architecture, we talked about the training process. How about the results? How well does intent actually perform?
Well, the authors evaluated intent on a bunch of different real-world data sets, and the results are pretty impressive. They looked at pedestrian data sets like ETH and UCY, an autonomous driving dataset called KIDDI, and even a more diverse dataset called SDD that includes pedestrians, cyclists, vehicles, all sorts of stuff.
And how did it stack up against the existing state-of-the-art methods?
It consistently performed as well as, and in many cases better than, other leading trajectory prediction models. And remember, it's doing all this with a much more efficient architecture. So that's a big win in terms of practicality.
So not only is it more accurate, it's also faster and less computationally demanding. That's a pretty compelling combination.
Exactly. And it's not just quantitative results either. They also did some qualitative evaluations, visualizing the predicted trajectories and comparing them to the ground truth. And visually, intense predictions just look more natural, more plausible.
That makes sense, right. If you're actually taking into account the agent's intention, you're more likely to predict a trajectory that a human would find believable.
Yeah, exactly. It's like
Wow.
The model isn't just blindly extrapolating from the past motion. It's trying to understand the logic behind the movement.
All right, now for the part I always find most interesting, the interpretability. Did the authors provide any insights into how the model is actually making these predictions? Like, is there any way to peek inside the black box?
Yeah, they actually did pretty cool visualization. They took the transformed trajectories from one of the data sets and overlaid them with the predicted probabilities for each intention class. So you can see, like, trajectories that were classified as left mostly have this clear leftward curve. And the same for right and straight. It's a nice way to see that the model is actually learning to associate those visual patterns with the corresponding intentions.
That's always reassuring to see, right? That the model isn't just magically spitting out accurate predictions, but that there's some actual logic behind it.
Yeah, it gives you more confidence in the underlying approach. And to further validate their design choices, they also did some ablation studies, which are basically experiments where you remove or modify different parts of the model to see how it affects performance.
So, like, what happens if you take away the contrastive learning component? Or what if you try using raw location coordinates instead of those extracted features?
That's the idea. And the results of these ablations really highlight the importance of each component of the intent framework. Like, if you remove the intention modeling, the performance drops significantly. And if you try to use raw coordinates instead of those carefully engineered features, it doesn't do as well either.
So it's really the combination of all these design choices, the intention modeling, the feature engineering, the efficient architecture that makes intent so effective.
Exactly. They all work together to create a model that's both accurate and practical.
Right. Before we move on to the novel notion segment where we brainstorm some future research directions, any other key takeaways from this paper?
Well, they also did a little bit of analysis on the model's sensitivity to different hyperparameters, basically tweaking those knobs to see how it affects performance.
And what did they find?
They found that the model is somewhat sensitive to those hyperparameters, but there's a fairly wide range of values where it performs well. So that's good news. It means it's not overly finicky.
Makes sense. All right, let's move on to the novel notions segment. Now, the authors of this paper focused on predicting the trajectories of, fairly generic road agents.
Yeah.
But in the real world, there's a huge diversity of agents out there, right?
Absolutely. You've got pedestrians, cyclists, cars, trucks, buses, motorcycles, scooters, skateboards, those little delivery robots, people walking dogs, people pushing strollers.
Right. And they all have their own quirks, their own ways of moving, their own intentions. So thinking about future research, how could we build on the intent framework to better account for this diversity of agents?
That's a great question. One idea that comes to mind is something like personalized intention modeling. Like, imagine if the model could learn to recognize that a cyclist making a sharp turn is behaving differently than a car making a wide turn, even though both are technically turning.
So instead of having a single generic model of intention, you'd have different models or different parameters for different types of agents.
Yeah, that's the general idea. Maybe you could even incorporate some kind of meta-learning approach where the model can quickly adapt to new types of agents based on just a few observations.
That would be really cool. Like, imagine a self-driving car encountering a new type of delivery robot it's never seen before. If it could quickly learn the characteristic movements and intentions of that robot, it could navigate around it much more safely and smoothly.
Exactly. And you could even extend this idea to individual agents. Like, maybe the model could learn that a a particular pedestrian tends to walk very hesitantly, or that a certain car always makes very aggressive lane changes.
So it's almost like building a reputation system for road agents. The more you interact with them, the better you understand their individual tendencies and intentions.
Yeah, that's a really interesting way to think about it. And it's definitely an area ripe for future research. I think the intent framework provides a really solid foundation for exploring these kinds of ideas.
Absolutely. It's a great example of how we can move beyond those purely data-driven approaches to trajectory prediction and start to incorporate some real understanding of the why behind the how.
I couldn't have said it better myself.
Well, that brings us to the end of our deep dive into the intent paper. Super interesting stuff. As always, we'll have a link to the full paper in the show notes for anyone who wants to dig into the details. And before we sign off, a final thought for our listeners. How do you think this ability to understand intention will shape the future of autonomous systems? Will it lead to safer roads, more efficient traffic flow, or maybe something completely unexpected? Let us know your thoughts in the comments. Thanks for listening to Talk Tensors, and we'll see you next time.